A simple light bulb and a very complex industry have one thing in common. They both cannot work without electricity. A consistent power supply is a backbone for any developed nation. But due to many issues, we can face electricity outages. It could be because of the lightning, animals, or strong wind. Electricity blackouts cost a lot for both big industries and the general public. In 2003, there was a power blackout in West Malaysia which lasted for 5 hours and it cost industries 13.8 million ringgit in the loss. In other words, consistent electricity is extremely important. We can't see the future, but we can study patterns and forecast possibilities. We used machine learning algorithms to create an ensemble model to predict possible power outages. At first, we plotted all the lightning data to get a feel for the available data. Here we can see the lightning data is scattered throughout all of Borneo Island. Using Python, we only kept lightning events that occurred within a 1 kilometer radius of the transmission line, which greatly reduced the number of lightning events. Lastly, we divided this filtered lightning data into two categories, trip and normal. The trip category denoted those lightning events which actually caused a transmission line failure, and normal described lightning events that struck within the radius but did not cause any power outage. We also combined rainfall and wind data based on the date and time of the lightning data. The table shows preliminary data analysis of trip and normal data. We can see there is a noticeable difference between their values. This suggests there should be a clear trend between the trip and normal data. After the data preprocessing and preliminary data exploration, the dataset was fed into Python and SAS. The Python solution is a combination of three machine learning algorithms. They are random forest, support vector, and linear regression. K-fold cross-validation was used to make sure the dataset is not being overtrained. For each machine learning algorithm, the result was 93%, 86%, and 87% respectively. The ensemble model created from combining these three models yielded 94% accuracy. The SAS model resulted in even higher accuracy, but because we could not perform K-fold cross-validation in SAS via, the Python model is taken as the standard. In conclusion, the created system is hoped to help electricity providers such as Sarawak Energy, who can improve their grid reliability and reduce downtime in fixing the tripping line by predicting power outage earlier. Though this current system is using very unfocused data, as we saw from the initial map plot, still the system was able to predict with good accuracy, which shows positive potential for the model. With more focused data, we can perform time series analysis, which would improve the current system tenfolds and allow us to get more detailed results. Lastly, a reliable prediction system can help save millions of ringgit for electricity providers, industries, and general users.